A very interesting event took place in the history of the Nobel Prizes. This year, while everyone was discussing predictions for the Nobel Physics Prize and weighing between Frederick Cosen's work on quantum lasers, Michael Berry's Berry phase, or Aharonoff's work on the Aharonoff bomb effect, the Nobel Committee surprised many by awarding this year's Nobel Physics Prize to a field that at first glance seemed unrelated to physics: machine learning. The winners of the prize were John Hopfield and Geoffrey Hinton, the two individuals responsible for the emergence of the field known as machine learning since the 1980s. Naturally, the news has caused quite a stir. Some are arguing that the Nobel Physics Prizes have lost their meaning, and many are lamenting that physics has hit a wall, leaving no room for groundbreaking research. But how should we interpret the decision to award this year's Nobel Physics Prize to machine learning, and more specifically, to artificial intelligence? Was there really no other deserving work in the field of physics this year? Or is there, in fact, a logical explanation for awarding the prize to AI? I have prepared all the reasoning and scientific background for you. In this video, you will find the origin story and scientific background of AI, and more fundamentally, machine learning. So, a deep analysis awaits you. Let's begin. First of all, we need to constantly remind ourselves that we are in a new era, something we have emphasized repeatedly. One of the first things we can say about this prize is that it is a testament to how artificial intelligence is breaking down disciplinary boundaries. But before making such a judgment, let's first examine the details. Let's start by looking at the official statement from the Nobel Committee regarding why the award was given to research in machine learning. This year's laureates utilized tools from physics to develop the methods that underpin today's powerful machine learning technology. While John Hopfield developed a system for storing and reconstructing information, Geoffrey Hinton invented a method that independently discovers features within a dataset, a method crucial to today's artificial neural networks. Now, let's delve into the steps that connect this explanation to physics. First of all, we are all quite familiar with computers by now. We have all witnessed how they translate texts, interpret images, and even hold fairly natural conversations. However, many are unaware of how this technology, which handles our daily tasks so easily, has brought about a major revolution in scientific research behind the scenes. One of the biggest challenges facing scientific research has always been dealing with enormous amounts of data. And the hallmark of this technology is its ability to classify, analyze, and interpret vast amounts of data, tasks that could take a human years, in mere days, or even hours. In this way, it has become a valuable tool for researchers. The overarching term for this technology is what we call machine learning. What we refer to today as artificial intelligence is essentially an extension of machine learning technology. And if you ask what constitutes the core of this technology, we could say it is the artificial neural networks that we are familiar with. While we are not yet at the stage where machines can think independently, they can perform memory and learning tasks with near-perfect accuracy. The individuals who won this year's Nobel Physics Prize are the ones who made this possible. So, what exactly did they do? As we mentioned, artificial neural networks are the foundation of everything. The inspiration for these networks, unsurprisingly, came from the journey to understand the human brain. In the 1940s, researchers began to understand the mathematical basis underlying the neurons and synapses in the human brain. Our brain's neural network consists of living cells known as neurons, which communicate by sending signals to each other through synapses. When we learn something, the connections between certain neurons strengthen, while others weaken. Around the same time, neuroscientist Donald Hebb's hypothesis about how humans learn supported this understanding. According to Hebb, synapses strengthen as neurons work together. Building on this work, researchers began looking for ways to simulate the neurons and synapses of the human brain using computers. Neurons in the brain were represented as nodes assigned different values, while the synapses between them were represented as connections between these nodes. These nodes are interconnected, and as the network is trained, the connections between nodes that are activated simultaneously grow stronger, while others weaken, just like in the human brain. Donald Hibb's hypothesis about learning is still used today in the process known as training artificial networks. By the late 1960s, however, technological limitations meant that progress in neural network research stalled, and many researchers began to believe that these networks would never provide any real benefit. The field was abandoned to such an extent that, starting in the 1970s, all work on neural networks was shelved, leading to what is now known as the AI winter. However, interest in neural networks was revived in the 1980s, with many significant ideas, including those of this year's Nobel Prize winners, making a great impact. One of the laureates, John Hopfield, first emerged on the scene. In 1982, Hopfield developed a method known as the Hopfield network, also referred to as associative memory. We can compare this method to an experience we've all had, when we try to remember a word, and it's on the tip of our tongue. The object or thing associated with the word is right in front of our eyes, and by bringing it to mind, we try to build scenes around it to eventually recall the word. Hopfield's associative memory works similarly. Here, it's important to mention that John Hopfield was a physicist. Yes, he had even used his physics training to conduct research in molecular biology. To further his work on neural networks, what did he need? A computer. Yes, we are talking about a time when computers were less powerful. He decided to move to Caltech, which had a better computer infrastructure. Hopfield also drew on his physics background, which provided him with new ideas. His studies on atomic systems helped him understand how interesting things can emerge from the interactions of many small parts. He especially benefited from his knowledge of magnetic materials, where every atom acts like a tiny magnet. Atoms next to each other influence one another, and sometimes they all spin in the same direction. Hopfield used this knowledge to develop a new model. In this model, just like atoms, the nodes were connected. These nodes influenced each other, determining the behavior of the network. In this way, Hopfield created a system that mimicked the workings of the brain using the laws of physics. The Hopfield network consists of interconnected nodes, each of which can take a value of 0 or 1, like the pixels of a black and white image. When the network is shown an image, the nodes and connections are adjusted to remember that image. When a new image is presented, the system tries to transform it into the closest image it knows. This process uses a calculation similar to the concept of energy in physics, adjusting the nodes until the system minimizes its energy. The system could remember multiple images and distinguish the differences between them. It could also be used to correct damaged or incomplete images. Of course, remembering an image is one thing, but understanding what it represents is a more complex task. Even small children can be shown different animals and correctly identify them as dogs, cats, or squirrels. Though they may sometimes make mistakes, over time, they almost always get it right. Children learn this by observing their surroundings, without learning concepts like species or mammals. And this is where the other laureate, Geoffrey Hinton, comes in. When Hopfield published his groundbreaking work, Hinton was working at Carnegie Mellon. He had previously worked in experimental psychology and artificial intelligence, and the question that always lingered in his mind was this: can machines learn in the same way humans do? Hopfield's work provided all the infrastructure he needed for this. Together with his colleague Taranovsky, Hinton developed a new method by building on Hopfield's network and leveraging statistical physics. Statistical physics studies systems composed of many similar parts, like the molecules in a gas. While it may be difficult to track each molecule individually, we can use statistical methods to deduce general properties, like pressure or temperature, for the entire gas. Using these ideas, they developed a new network, which used the equation developed by the 19th century physicist Ludwig Boltzmann. This method, published in 1985, was called the Boltzmann machine. Moreover, the Boltzmann machine learned from examples, not instructions. During training, the values of the network's connections were constantly updated, increasing the likelihood of the examples shown to the machine. The more frequently an example was repeated, the higher its likelihood became. This training process also enhanced the machine's ability to recognize new examples with similar features that it had never seen before. An example of a trained Boltzmann machine can be likened to recognizing that two people are related when we meet a friend sibling for the first time. It could identify new examples belonging to known categories in the training material and differentiate between unfamiliar examples. Initially, the Boltzmann machine was quite inefficient, and it took a long time to find solutions. However, Hinton continued to work on improving this machine. In later versions, certain connections were removed, making the machine more efficient. In the 1990s, while many researchers lost interest in artificial neural networks, Hinton was one of the few who continued to work on them. In 2006, he and his colleagues developed a method for training a network by layering a series of Boltzmann machines on top of each other. This pre-training method provided a better starting point for the network's connections, optimizing its training for tasks like image recognition. The Boltzmann machine was often used as part of a larger network. For example, it could be used to recommend films or TV series based on the viewer's preferences. Since the 1980s, the work of John Hopfield and Geoffrey Hinton had laid the foundation for the machine learning revolution that began around 2010. This development was made possible by access to large datasets and the tremendous increase in computational power. The artificial neural networks used today are typically very large and multi-layered. The training method for these deep neural networks is what we call deep learning. Hopfield's 1982 paper is a great example of understanding the scale of this progress. Back then, a network with 30 nodes was used, and fewer than 500 parameters were tracked. A network with 100 nodes was considered too complex for the computers of that time. However, today's language models can contain trillions of parameters. Currently, researchers are focused on developing the application areas of machine learning. It is still unclear which fields will be the most effective, and there are ongoing ethical discussions regarding the development and use of this technology. Physics has not only contributed to the development of machine learning, but has also started to benefit from artificial neural networks. Machine learning is now being used in fields such as the discovery of the Higgs boson, reducing noise in the measurements of gravitational waves from colliding black holes, and searching for exoplanets. In recent years, this technology has also been applied to calculate and predict the properties of molecules and materials. Examples of this include calculating the structure of protein molecules or discovering new material versions with the best properties for more efficient solar panels. Thus, the awarding of the Nobel Physics Prize to this work marks a significant turning point and reminds me of something. Physicists also had a hand in the invention of the transistor, and the world's transformation since then is evident. Today, once again, we are talking about a revolution, with physics behind it. A technology inspired by physics is helping us solve the hardest problems in physics. Tomorrow, we will witness the breaking down of interdisciplinary walls on this journey, which ranges from modeling the smallest organisms to modeling the human brain and, ultimately, the universe. What do you think? Considering all of this, do you think it was fair to award this year's Nobel Physics Prize to these individuals? Please don't forget to share your comments. Thank you for being here, and I look forward to seeing you in the next video. For now, take care.